Running Man.
Bad.
All right.
17.4/5 is resistance. Today we're going to talk about resistance, resistivity, and be able to calculate resistance due to temperature changes. And we're not talking about extreme temperature changes. We're talking about little temperature changes within, a couple hundred Celsius, not like the huge ones, because those tend to not be linear. All right, so we've got some dead guy up here. George Simon Ohm. So ohm is what we measure resistance in ohms.
Positive and
Named after a guy. Here's a picture of the guy. This was between 1787 and 1854. He developed the concepts of resistance. So you can think of resistance in a circuit. It's very similar to like air resistance, kind of. And he figured out this proportionality between current and voltage, which he called resistance. So, the wire resists the flow of the electrons. This is called resistivity. We also can get these things called resistors and put them into the wire, and it will increase the resistance of that. Now, the resistance is caused by charge carriers bumping into fixed materials in the wire. So your hand is bumping into the air atoms. The air slows your hand down as you move through it. It doesn't slow down much. Think about putting your hand in water. It's going to slow down a lot more as you move it. So this is the same idea, except for electrons are a lot smaller. And they bump into these molecules in the wire instead of moving around them. And that is what's going to slow them down. Yeah.
Was this the last test we did?
Mm-hmm.
Yeah, I did one before that.
Okay.
I like this code resistivity.
All right, now Ohm's law. He was relating potential difference to current, and he found that that's resistance. So our equation for us is V equals IR. Now remember, when they write this, it's usually delta V. Okay? Just V. V delta V, the same thing. I just cheat and call it V equals IR because I don't want to confuse you. So V is our potential difference, or our voltage, measured in volts. I will be our current in amps, and R is our resistance in ohms, which this is a capital omega, and that is representing ohms. And if you have a hard time remembering this equation, remember ver, as in ver, it's cold in here and you're Russian. No, something like that.
And wait, in your Russian?
In your Russian.
Like, when you were cold, you were big to be cold. So, that's Russian.
Well, you should see the one that I have for P equals IV. That one's coming up soon.
Or we can make it like wired,
Wire.
and it runs wired.
Wire.
Or it's just a
But then you'll
guy
want to
saying
then you'll
wire.
want to put an E on the end of it.
You could be like, no,
Why don't you like my ver?
you could
I
be
do
like,
like I'm gonna get it.
Ohm might have been German, so he might have been via.
Or you can be like meditating on how did that Oh, that's what that portion is supposed to do.
Oh. Mm-hmm. We're good. All right. Resistivity is resistance, but this is when you're trying to figure out what the wire's resistance is. So resistivity. It's a property of the wire. R will be the resistance in ohms. Your rho there is the resistivity, so that's how resistive is the wire. And that is going to depend on a couple of things: how thick the wire is, what the wire is made of. Actually, it's pretty much just what the wire is made of. There is a table in your book where you'll look up these constants. If you need the constant, it will be given on the test. It's different for each wire. So aluminum wire versus copper wire is going to have a different resistivity. Again, that's a rho. In case you're wondering, it looks like it's kind of like a curly P. Rho. Wait, I have to draw it correct. There we go. Rho. That's rho. Resistivity. It's on page 577. Your L is your length of the wire, and your A is the cross-sectional area of the wire. It'll either tell you the cross-sectional area of the wire, or it'll give you the radius of the wire, and since a wire is a circle, you'll just use the area for a circle pi r squared, and then plug in your r.
So just to check, this is the part above A again? The
L, that's the length of the wire.
Oh, yeah.
Okay. Benji, did you have a question? Okay, yeah, so length of the wire.
I finally learned how to draw that pizza that's rounded, not blocky. I have to draw it backwards, like I have to draw it from the inside out instead of going from the tail up and around.
Oh, yeah, that's...
You go like this?
Well, you draw it like you would a capital cursive L. You just don't finish it.
Whoa. I just noticed that a capital cursive L is like 2 rows. Like,
Mm-hmm.
like, whoa. That's cool. It's like row.
I need more blue Expo pens if anybody wants to bring some to me for late passes.
Wait, you need blue?
Yeah.
Wait, so like that, you don't just buy this in the store, you buy Expo markers and put it inside it? What? Yeah, that's really great. This is like refund.
And I like the ones that aren't chisel tips, the ones that are pointed tips. Because the chisels, that's why this one's broken. It's because the little cap is really tiny and it slices. Okay, good? We're good? All right. So here is how resistivity and resistance work with temperature. So they're the same equation. So whether you have resistivity or resistance, you just plug it in there. You need two to compare. You've got to have some like original. At this temperature, the resistivity is this. So if I increase the temperature by this much, then I could figure out what the resistivity would be at the next temperature. So you have to have like a baseline. That's what these knots are for. So we have our resistivity at whatever temperature your new temperature is. The original resistivity, 1 plus. Now alpha, this is that coefficient of resistivity for temperature. It's also on page 577, I believe. A lot of the times they'll say, okay, the resistivity at 20 degrees is this, so you put 20 degrees into the matching. So their R naughts are at this initial point, and then the ones without the R naughts, the rho and the T without the R naughts, are the final point. And the same thing goes with resistance. So you have to have that baseline. Again, alpha is something you'll look up. If it's on the test, they'll give it to you.
Yeah. Changing the temperature.
Right, so if they don't give,
What?
if they don't give us temperature, are we supposed to assume that T is 20?
Yeah, you can do that. You can say that it's 20, but it'll give you the resistance, the resistivity or the resistance at 20. It'll give you some baseline.
Okay.
Yeah, it should be included.
Okay.
It's not something you should have to guess now.
Yeah. Changing temperature looks like someone crying.
It does kind of, doesn't it? Maybe that's just your inner child, like, crying from all this physics. It's adult math.
Oh, you make that really sad.
Okay, so T is in Celsius.
See, T is in Celsius or Kelvin, but you can be left in Celsius here. Yeah, this would be a change in Celsius, so a change in Celsius and a change in Kelvin are the same thing. So they're, they go each go up one at the same time. Yes.
Change in Celsius and change in Kelvin are like the exact same number. Yeah.
Correct. Yeah. Which is why these are those ones are fine right there. Same thing when we did heat. So we didn't do heat in Physics 1, so you guys don't have that reference, but all my other classes do. Yeah. like 273.25 or 15 or something.
So it's only
Yeah. But as far as I know, all of your questions are in Celsius. Okay. Any more questions on this one? No. All right. Temperature and resistance. The higher the temperature, the higher the resistance. And this is because the molecules in the metal are vibrating around more, so they tend to block more of the electrons. Like, I don't know, in soccer, how the goalie moves back and forth in there. It's harder to get past him because he's in the way more often. I guess, I don't know. Not really a sports person. How that works. Figure someone here know what I'm talking about. Yeah, is that right? Yes. I said that's fine. Okay, it works. I just made that one up. I didn't even know if it was true. Okay, we're good, we're good. All right. So, see how easy that was? This section's so easy. I just don't want you to go very far in depth. So, here's our first clicker question. It says number 10 copper wire, it has a radius of 1.3 millimeters in case you were wondering, is commonly used for electrical installation in homes. What is the voltage drop in 40 meters of the number 10 copper wire if it carries a current of 10 amps? It gives you the resistivity.